Supernovae are extraordinarily intense explosions that happen at the end of some stars' lifetimes. They are so bright that for a while they can outshine the entire galaxy that they exploded in. And there are a handful of observations of supernovae that have exploded in our galaxy throughout history. The most recent one that could be observed in daylight with the naked eye was observed in great detail by Johann Kepler in 1604. Prior to that, another supernova was observed in 1572 by Tycho Brahe. In his youth, Tycho was involved in a sword duel over the legitimacy of a mathematical formula which neither party could prove was right. In this duel, he lost part of his nose and forevermore wore a replacement made of gold and silver and held on with glue. But back to supernovae. In 1054, Chinese astronomers observed what they called a guest star, and their observations of this were precise enough that we now know exactly where this supernova exploded, and this is what it looks like today. It's known as the Crab Nebula, and at its centre is a pulsar, a special type of neutron star that was left behind after the supernova explosion. We'll look at pulsars in another video. There are a couple of different types of supernovae, but we're going to look at core collapse types, which is what ultimately happens to stars who are at least 8 times more massive than our Sun. For most of a star's lifetime, it fuses hydrogen in its core. Hydrogen is fused into helium, releasing the energy that makes the star shine and keeps it held up against gravity. When the star runs out of hydrogen to burn in its core, the core begins to collapse because there is less pressure pushing out than gravity pushing in. This collapse causes the core to heat up and get denser. This increase in temperature and density allows the helium in the core to fuse into carbon and oxygen. This stops the collapse because it again increases the pressure pushing out to balance the gravity pushing in. This cycle of running out of fuel, collapsing, heating and starting to fuse a new fuel continues until the star is left with iron in its core. Iron can't fuse into heavier elements and release energy because it is too tightly bound. So the iron in the core collapses and gets hotter and hotter and denser as it collapses under gravity. But suddenly the core has to stop contracting because it reaches near nuclear density and it is not possible to contract any further. This sudden stop causes a bounce back which sends a pressure wave through the rest of the star which throws off its outer layers in an amazing explosion. It is the remnants of these supernovae that the CTA will be looking for. As the expanding supernova remnant crashes into material surrounding it, particles are accelerated to such high energies that gamma rays are produced. And because these supernova remnants are the sites of such energetic particle acceleration, they have been proposed as the site of origin of at least some of the cosmic rays which arrive at Earth. Cosmic rays are exceptionally high-energy particles, mostly protons, that continually bombard the Earth. Their origin has puzzled scientists for over 100 years. The CTA will help scientists understand particle acceleration in supernova remnants, and so help them understand where these cosmic rays come from. There's another reason why supernovae are really important to all of us. They're the only things in the universe that spread heavy elements into the rest of the universe. So elements up to carbon can be made in slightly less massive stars, which never go supernova. But these stars lose their matter in a stellar wind, and half of all carbon is thought to come from these stars. And then elements up to iron are made in a star before it goes supernova. And then heavier elements, such as gold and silver that you might wear in your jewellery, they are only ever created as the supernova explodes.